All right, so we're looking at 5.3, definite integrals and antiderivatives. Just as a kind of word at the front here, we're not going to really get any kind of formulas for computing integrals in this section. We're still looking at an integral as being the area that's underneath a curve. And in this section, mostly what we focus on is the geometric shape that the area takes on, and trying to find the area of that geometric shape just with our formulas from geometry. Okay, so hopefully that makes more sense as we move on. So for starters, they give us some properties, and I'll kind of explain them as we go through. So the list of givens, we have the integral from 1 to 9 of f is -1, and then from 7 to 9 of f is 5. So this is the same function f on different intervals. So these are x values when x is 1 all the way up to x being 9, and over here we have x being 7 all the way up to x being 9. And then they give you a different function h, which is the integral from 7 to 9, coming out 4. So these are going to be our three givens that we use to try to answer a whole series of questions. There's another slide too. So for part A, it asks you for the integral 1 to 9 of -2 times f of x dx. So as one of the properties here that we're supposed to be going over, the coefficient can be pulled out in front of the integral sign. So if I find out how much area is under the curve of f between 1 and 9, I can just multiply that by -2. And so up here, they flat out tell you it's -1. So this integral evaluates to -1, multiplied by -2, I get my answer. Part B, what if you wanted to add the two functions together? And this is 7 to 9. When you're adding them, they both have the same interval from 7 to 9. So I'm looking at this interval, not the previous one now. And so the property says that if you want to, oops, sorry, go back. If you wanted to find the area under the curve of the sum of them, it's the same as if you find the area under each of them separately and then add them up. So I'm just going to break this up. It's kind of like distributing your integral sign. Excuse me. So the first part, I plug in the 5, and the second part, I plug in the 4. So again, 5 and 4 from up here. Okay, so I get 9. And then for part C, they're kind of just putting these two properties together. So this idea that the coefficient can be pulled out in front, and the fact that when you have a sum, you can do two separate ones, they just combine that. So this 2 gets pulled out in front of f of x's integral, and -3 would get pulled out in front of h of x's integral, and they're both on the integral 7 to 9. So I just look up on top and plug in these numbers. I get my answer. I put these properties should make sense graphically too. So you want to be thinking about some function f of x on the interval from x equals 1 to x equals 9. So you could draw this and actually kind of picture it. Okay, so this is a continuation. So picking up from where we left off, it's now part D. And it has the integral from 9 to 1 instead of 1 to 9. So when the limits on the integral sign are flipped over, you can flip them back and put a minus sign out in front. So just something to remember at this point. If you flip the limits, make sure you put a minus sign. So when we're looking at integrals, we always prefer to have the smaller number on the bottom and the larger number on top. So this one up here looks kind of lopsided to me. I would much rather see it with the minus sign out in front and have 1 to 9, smaller number on the bottom. Oh, I keep doing that. Okay, so anyway, looking at this one, I just go back up here and say, oh, it was -1, so negative of -1. And then part E, it has 1 to 7. Well, notice that none of these go 1 to 7, so you have to be a little sneaky about it. So I'm picturing the area under the curve from 1 to 9, and this one over here, same function, but it's the area under the curve between 7 and 9. So I figure if I have this entire interval 1 to 9, and I subtract off the far right part that's 7 to 9, then I should have 1 to 7 left. And that's exactly what I have set up here. So my integral of the whole interval from 1 to 9, subtracting off the part I don't want, which is 7 to 9, and I'm going to be left with the integral of 1 to 7. That's what I'm asked for, and so that looks good. Plug in my values. This one, same kind of thing. I want to flip my limit, flip my integral over, so it goes 7 to 9. When I flip it over, I have to put a minus sign out in front. That's our property. And then I can take each of these separately and subtract at the end. So again, once I flip my integral over, it'll be a negative h and a positive f. So here's my negative h and my positive f. Okay, plug in values and you've got it. Okay, the next big concept in this section is the average value or mean value theorem for definite integrals. Now remember, there's a mean value theorem for derivatives that we've already talked about, which had to do with your secant line slope and so forth. But this time we're looking at average value. So if I look at my picture that I've sketched down here, an average value, f average, is a y-coordinate. And it would be the particular y-coordinate, so that if you were to draw just one rectangle with that height all the way across the interval, the area under that line, or area of that rectangle, would be the same as the area between the x-axis and the curve. So the question is, how high would that rectangle have to be? Let's see, I guess I might as well, oh, let's see, where'd my draw tools go? Hold on a sec. Okay, so here's my drawing tools. If I come over here and let's pick black. So how about if I have A as right here, we'll call that A, and then B, let's see, over here, I guess I've already got it selected. So if I come down here and say B is right there, okay, the area that's in this region, I'm looking for F average. So I'm looking for the height that I could draw just a single rectangle that would have the same area as the area in this space here. So if I just kind of eyeball it and picture maybe the height of that one rectangle would need to be right there, well then I come over here and I would call that spot right there F average. Okay, and so again, this rectangle down here, all this area down in here, whoa, is going to be the same as the area underneath the curve itself, well, between the x-axis and the curve. All right, well, that was a little messy, but we'll leave it at that. So anyway, our formula then is going to be that you have the area under the curve of f, and you multiply that by 1 over b minus a. b minus a, again, that's just your interval that you're looking at. So b minus a is how wide your rectangle is. So if you take your area and divide it by the width, 1 over means divide by. So take the area, divide it by the width, what you should get is the height. And so here's my y-coordinate, the height of my rectangle. Okay, so one to try that with. They give us a parabola shifted to the right by 1 on the interval from 0 to 3. It says find the average value of the function on the interval, and at what points in the interval does the function assume its average value. Okay, so here's our formula at the top, and I just go straight to plugging things in. So 1 over, and this is my a and b, so plug those in. Integral, again, a to b, and my function. That part all makes sense, but at this point then, how do you actually figure out what this integral part equals? 1 over 3 minus 0, no problem, that's 1/3. But this integral part, we haven't really talked about any of the formulas. We have done in previous chapters the antiderivative, where you had to kind of think backwards from derivatives. So this would be a power rule. I did it off on the side. I'm going to use capital letter F to show that I'm integrating my function. So if I integrate this thing, I'll get capital F. And it should turn out to be, if I add 1 to this exponent, the opposite of power rule. So it becomes a 3, and I would divide by that 3. You can see the 1/3 out in front. There's no chain rule that would have occurred because, again, the coefficient of x is 1. So my chain would have just been a 1. So if you want to check and make sure that you did your antiderivative correctly, you just sit there and take the derivative of what you think is the integral. So if I take the derivative of this, my power rule would say 3 comes down. 1/3 times 3 is 1. Rewrite the inside, subtract 1 from the exponent, making it a 2, and then multiplying by the derivative of the inside. So it sounds like it all is going to check. So now we have these limits on the integral sign from 0 to 3. Well, I'm going to go ahead and just kind of go through a sneak preview, I guess, to section 4, which is the fundamental theorem of calculus. If I want to integrate this on the interval 0 to 3, then I get my antiderivative, and the nice thing fundamental theorem is that all you got to do to evaluate it is plug in the upper number first and then plug in the lower number and subtract your two values. So if I plug 3 in for x, I got 8/3. If I plug 0 in for x, I get negative 1/3. And so I do this one minus that one. So again, capital F of 3 minus capital F of 0 would just be 8/3 plus, minus a negative, or plus 1/3. Comes out 1. Okay, so F average, meaning the y-coordinate, the average height on my interval would be 1. And then it does ask the second part, at what points in the interval does the function assume its average value? So if you know that y is 1, it's just asking you what is x. So maybe I made it look more complicated than it needed to be. Here's my function. If my y value is 1, I just plug 1 in and solve for x. So here it is. I plugged one in over here and solved for, I called it C just because it's some particular value. And I ended up getting two different spots. So there's two places that the mean value theorem holds for this problem. Okay, moving on. So for this one, it asks you find the total shaded area and the net area. And I didn't actually shade it yet, so let me go ahead and do that. And they're talking about the area that's down below the x-axis. So I'll go ahead and kind of shade in down here. And then above the x-axis, but under the curve. So kind of right up through there. So those two yellow areas is what we're trying to find the area of. Okay, so for region 1, I'm going to call that, oops, there we go. So region 1, sorry. Region 1 is going to be the part down here that's below the x-axis. So it runs between 0 and 2 on the x-axis. So my integral is from 0 to 2. Then I have my function. And when I integrate that, again, I do my antiderivative. So add 1 to the exponent and divide by that new exponent. This one, add 1 to the exponent, makes it x squared. Dividing by a 2 for the new exponent, I get 2 over 2, which is 1. And then what I was saying before about the fundamental theorem, you're going to plug the top number in first, so f of 2 minus, and then plug in the bottom number, 0. So if I plug 2 in for x, I get 8/3 minus 4, and then when I plug 0 in, it's just 0. Okay, for region 2, that's this area over here, same kind of thing. So fundamental theorem, it's going to say go ahead and do the antiderivative, which is this line here, and then the fundamental theorem, second part to it, says to evaluate, you plug in the top number first for each of the x's, and then subtract what you get when you plug the bottom number in for each of the x's. So the 3 goes in first, subtract, then the 2 goes in. And so when I plug 3 in, 3 cubed over 3 minus 3 squared, and then minus, and then plug the 2 in, 1/3 of 2 cubed minus 2 squared, and solve it out. So I get a negative 4/3 and a positive 4/3. Well, I know in the previous section we said if the area was below the x-axis, then we would call it a negative area. So either I'm going to allow this to be negative and this to be positive, and I would get my net as 0. Negative and positive cancel out. So the net area comes out 0. Or I could go ahead and think of it just in terms of absolute value. What's the total area? Well, I don't care that one's negative and one's positive. If I just want the total area, I do absolute values of each piece, and I get 8/3. Okay. I think this is going to be a good place for me to break the slideshow, just because I can't post over 15 minutes on YouTube. So this is part 1. You'll have to open up the other one to see part 2. Okay.